Okay, first of all, I'd like to thank the people at the Institute for inviting me. It's an honor to be in such distinguished company. So this is what I want to talk about today, the criticality hypothesis. What do I mean by that? Well, really, does it matter if the brain is critical? And in order to explain that, I want to talk about three subtopics. First of all, what does it mean to be critical in physics? And I'll spend some time going through a tutorial just kind of explaining what the concept is so we really understand it. And then, is the brain critical? So I have to talk about neural data. Does the neural data fit into this model or this idea of being at the critical point? And then finally, why should you care? Does it have any implication at all for human health or for the human brain? Okay, so let's get to the first point, the critical point. Now, criticality is an emergent property. So it's something that happens when you put together a bunch of parts and the whole is more than the sum of its parts. So what I'd like to do is take a look at a very simple system, just a magnet, and see some of the emergent properties that come around there. So a ferromagnet can be considered a lattice. And in that lattice, you've got lots of little spots, and at each spot, you have something like a bar magnet. It's a spin that can either point up or down, and that's indicated by these arrows here. Now, normally, when these guys are in a lattice, what they tend to do is have nearest neighbor interactions. They tend to all point in the same direction. They favor that. It's low energy. So that's what they'll tend to do, as long as the temperature isn't too high. And in some simulations, I'll represent these different pointed arrows by either black squares pointed up or white squares, meaning that the arrow is pointed down. Now, what happens if you have different temperatures as you move this system into different regimes? Well, the first, somehow I jumped. Let me go back. Right here. Okay, there's three regimes. So when the temperature is very low, what you have is the nearest neighbor interactions dominate, and then all of the spins tend to point in the same direction. And there, it's like there are lots of tiny little bar magnets. You have some net magnetization for the sample. So it can stick to your refrigerator. It's a magnet. Now what happens if we heat it up? If we heat it up a lot, then that's like adding thermal energy. It's like you're shaking the lattice. And now these little spins jumble in many different directions, and they cancel each other. And so you have no net magnetization. And so it won't stick to your refrigerator anymore. It becomes very disordered, whereas over here, it's very ordered. So somewhere in the middle, you've got some interesting things going on. This is where you'd have the complex regime. At the critical temperature, what you have is local pockets of order, where you might have some of the spins pointing in the same direction, but then you've got diversity. I was going to say complexity, but yeah. So diversity of things. You've got another domain nearby that's pointing in a different direction. So you've got variety and local order mixed together. And many people think that this is where complex behaviors or emergent behaviors would arise. So what does this look like if we simulate it? Well, let's take a look at the low temperature first. So this would be the subcritical regime. And remember, the black represents spins pointed up, and the white represents spins pointed down. So what happens if this is at low temperature, and we let this system kind of go to equilibrium? Well, what happens is the nearest neighbor interactions dominate, and so everybody points in the same direction, whether it be up or down. And you see, it's sort of a peer pressure type thing. It pushes out things that don't fit in the neighborhood. And eventually, if we let this run long enough, it would all either be pointed up or pointed down. And that would lead to net magnetization. That's when the sample has a low temperature. Okay, well, what happens if we go to the regime where it's very, very hot? Now we're shaking it, we're giving it lots of thermal energy. What's going to happen there? Well, you can probably imagine. No order at all. It's totally random. Because we're adding all this thermal energy, the nearest neighbor interactions, which are still there, are overwhelmed by thermal energy. And so now it's just totally disordered. Okay, and now the interesting critical regime, where you've got this balance of the thermal energy that you're adding and the energetic favorability of nearest neighbor interactions. They're just about balanced. So here, if you take a look at it, you see it's not totally disordered, but it's not ordered either. You've got these little blobs that persist for some time. They extend tendrils and pull them back. It almost looks like an amoeba moving around. And so here, interesting emergent properties occur when you get this balance of the two forces. This is the critical point, broadly speaking. But now what we want to do is we want to quantify it and see what types of equations apply to that. Sorry, I've got to show a few equations. Okay. So one thing we could measure, if this is, after all, going to be a model of the brain, is how one site might communicate with another. How do they correlate? And so we could take a look at a pixel in this simulation, let's say pixel A, and then look at pixel B, some other spot, some distance away. How would they correlate? So here's my equation. So what we'll talk about is a spin at site I and another spin at site J. And what this represents is basically, I'm going to move over here. This is the average of what's going on in site I, and this is what's going on at site I at any particular time. So this bracket here is the fluctuation. How much does site I deviate from its average? And then likewise over for J, you have the same thing. How much does it deviate from its average? Those are fluctuations. Now, we're only going to get a strong value of correlation if we have two things. We have to have fluctuations. They've got to deviate from their average, so that's non-zero. And they need to be coordinated. When one spin goes up, the other should also go up. When one goes down, the other will go down. Otherwise, you won't have a positive product here. So you need fluctuations, and you need those fluctuations to be coordinated. Okay, so let's take a look at what happens when you take this over time in the three regimes. Let's start with a low temperature regime. So at low temperature, time is going along the x-axis there. What you find, and this is the angle of the spin if it's pointing in some different direction, what you find is that you get very little fluctuations. So they tend to point in the same direction when it's all ordered, but there's no fluctuations. So the value of the correlation is low. However, when the temperature is very high, you've got plenty of fluctuations, but they're not coordinated. These things are bouncing in different directions. And so again, the value of the correlation would be low. Now, somewhere in the middle, where you've got the critical temperature, you have enough energy being added so that you actually have fluctuations, but not so much that it overwhelms the nearest neighbors. So now you have coordination. It's almost like one of those amoeba-like structures would go across the screen. It would flip one spin, and then it would flip another. And then as it left, it would kind of flip this out and then flip that down. So as these things move, you actually get coordinated fluctuations. And so the value of correlation there is very high right at the critical point. And that's what we see here. So let's take a look at another thing, because I want to quantify this and measure the critical point and go beyond just movies. But let's take a look at the correlation as a function of distance. So now I'm going to take a look at one site and how correlated is it as I move away, just in this simple simulation. When the temperature is low, you don't really have long correlations. When the temperature is high, you also don't have correlations over much of a range either. But at the critical temperature, what you have is correlations that extend for a very long distance. Here, maybe about 15 lattice sites, even in this simple simulation. So what this means is we've got a correlation length now that is much longer than the nearest neighbor interactions that were built into the simulation. All we did was couple nearest neighbors. Now we've got a correlation length that's 15 units long. That's a simple example of an emergent property. Now, if we had an infinitely large model, and if it was tuned exactly at the critical point, the correlation length would be infinite. It would diverge. So interactions across all scales could possibly occur, leading to the most complex behaviors, right at that critical temperature, right in between the two regimes of order and disorder. So here we can plot the correlation length as a function of temperature. We've got low temperature, critical temperature, and high temperature. And what we find is we've got a phase transition. This sharply pointed curve shows that we've got a boundary between a region where there's order, that's where the temperature is low and everything's pointing in the same direction, and disorder, where the temperature is high and everything's pointing in different directions. Now, if we had a very large system, this peak would be extremely sharp and go infinitely high. So it's a very distinct boundary between these two phases. Now, later on, we'll talk about how this might apply to the brain, and what we'll talk about are information processing functions. Those processing functions will show some sort of optimal curve like this, right at the critical point. Information transmission, storage, computational power, everything like that will be best right at the sweet spot. Okay. Am I clicking this somehow wrong? Oh gosh. How's that? There we go. All right, yeah. I'm at the critical point myself. Okay. So let's take a look at the correlation over distance. I feel so much better, man. Okay. Correlation over distance, if we were to go back and plot it like this, what we'd find is it's a curve. Now, I'm going to change the axes on you. I'm just going to make them log scale. okay? So when we do that, even in this crummy little simulation, you see something that looks almost like a straight line. And if I were to take a line there, you get what's called a power law. So what I mean by that is that the correlation scales as the distance raised to some negative exponent. So that negative tau is going to be the slope of that line. So you get something like a power law. So when things are at the critical point, you should get power laws. And if the system were infinitely large, that line would just keep going. It wouldn't cut off like I had in that simple simulation. And then if the system is subcritical, it'll curve downward. So we'll get that. Okay, so is that all you need to show that a system's critical, is just a power law? Well, the answer is no. What you really need is something like this. You want to show several power laws. And I'll just mention this, but there's something called the specific heat. It will also follow a power law, the magnetization, and the susceptibility. Don't worry about that. It's just lots of power laws, and they each have a different exponent. And you should get something like this, an exponent relation between these power laws. You put these exponents together and they form some simple equation. They're all interlocked in some way. Those are the true hallmarks of a critical system. So to summarize, in this tutorial on criticality, there's two main things. You have some optimum point, and you'll also get types of power laws that should be related to one another. Okay, so much for the magnet. Our brain is not a magnet, I can assure you that. So what's the neural data that'll tell us that this might be a reasonable picture for looking at the brain? Okay, so as Lee Hood has pointed out, you often need to have extremely high technology, cutting-edge instruments to really find out what's going on. And so I've collaborated with Alan Littke. Alan Littke is a particle physicist at CERN. He developed these things called silicon strip detectors for the collider halls. They've been used in finding the Higgs boson. And somebody convinced him a long time ago to use them for neural tissue as well. And they've done lots of experiments in the retina with E.J. Chichilniski using this. So here's a culture where you can put a slice on there. 512 electrodes. They're very tightly packed. They're either 60 microns or 30 microns together, so that's well within the distance of synaptic connectivity range. So we enhance our chances of recording from connected neurons. We can record at very high temporal resolution because they're electrodes, so sub-millisecond precision. And we can record for 8 hours or more. We just got tired and went for pizza and we shut it down, but it could just, in principle, keep going. It's a culture. Okay, and here's a quick little movie of like 100 milliseconds of data. We can now record over 500 neurons for hours at a time. So we get extremely rich, detailed data sets, the kind of things you need to do to evaluate statistical hypotheses. So one simple thing that we can do is we can look at the sequences that occur. So let's take a look at a cascade from that movie. Some neurons become active, you see a cascade of activity, and then it dies out. The size of that would be, let's say, 11 neurons. They become active in that cascade. What does a plot of this look like? Well, if we take the data and we just shuffle it, we randomize it, what you get is a plot that looks like this, where here the y-axis is the probability of observing a certain sequence size, and the x-axis is the sequence size itself. You'd rarely get anything larger than 10. 10 neurons occurring in a single sequence. Well, what we get in the data is actually something like this. We get a power law. So that was very exciting. And the power law says that the probability of observing a sequence of size s scales as s to some exponent. Okay, so when we first observed this, we were very excited. This is back in 2003. I was working with Dietmar Plenz, and we used local field potentials on a 60 electrode array with very broad spacing, 200 microns. So it suggested that maybe the brain was operating at a critical point. So I got all excited. We submitted the paper. It was well received. And then, as usually happens in science, somebody comes to mess up your work. No, it's really the critical nature of science, which is good, right? So we started receiving criticism on it. And this was healthy criticism and helped us to refine our ideas. So one of the biggest critics is Alain Desteche, and he's really helped us. And he said, look, you can get power laws easily. You have some random process that fluctuates and you just cut a threshold. The return times as it crosses the axis, those are distributed as a power law. So they simulated this and they could get power laws a lot like our data, which caused me much consternation for a while. You know, you got to go back to the lab, you got to think, how am I going to figure this out? So that was one of the criticisms, but also around that time, Mark Newman was publishing papers that were saying, hey, look, there's lots of power laws out there, and there's lots of ways to get them. You see here word frequency, English language, and that's for any language, really, citations and papers, web hits, books sold, telephone calls, earthquakes. So there's lots of things. It's power law, schmower law. It's like the Gaussian distribution of the 21st century. Everyone's got one. And there's lots of ways of doing this. A simple example is successive fractionation. You can take a stick, break it randomly at one spot, then break the components again randomly. You just keep doing this recursively, you get a power law distribution of length sizes. So there's many, many ways of getting it that don't have anything to do with being at the critical point. So we had to really evaluate this stuff. So how are you going to evaluate whether you're really at the critical point or not, or whether you just have a lucky power law? So here's what you need. You need to have multiple power laws. You need to show that these power laws are related in an exponent relationship. And if you're really fortunate, you can even get something called a universal scaling function that will reveal the dynamics of the system. So using the high-quality data that we collected with Alan Littke in collaboration with Karen Dahman at University of Illinois, we were able to reanalyze the data. And what we showed here is that this is the average number of neurons that fire, and this is the duration of one of these avalanches. That follows a power law. It's got a different type of exponent. And it turns out that you can then relate these exponents in an exponent relationship. So if that's the exponent for the avalanche size distribution, and that's for the avalanche lifetime, then it gives us this, something that tells us about the dynamics, but it also tells us about the height of the avalanches. So what do I mean by that? So this all works. So here's the height of the avalanches. Let's say we take one of these little cascades. I can get an envelope of its shape. How many neurons start out, and then over time, usually what happens is you start out small, it goes up, and then it dies down. You get these inverted parabolas as the shape of the avalanches. And if we get lots of them, let's say we have thousands of each of these, let's say thousands of something like 70 milliseconds long, we take all the avalanches that are 110 milliseconds long, we group them, and we get the average with the error bars. And then the idea is that somehow the exponents in those other power laws should let us to collapse these shapes onto one another. In other words, to show that they're fractal copies of one another, that they're really kind of just mimics of one another, and that's something that will only happen at the critical point. So it turns out that if we use those exponents, we do get something called avalanche shape collapse, which is a very good indication, a strong indicator that you're really not lucky here. Also, if we jitter the data by a tiny amount, 10 milliseconds, this whole thing falls apart. So it's a very precise picture of how the dynamics of neuronal avalanches unfold. It ties it all together to show that it is indeed a critical system. And the other thing I want to mention about this is that not all of our data show this. We get some that show power laws, but when you try the avalanche shape collapse, you don't get it always. So this is the most stringent picture of avalanche of criticality. The sign that you can do this is showing that you're really very much close to the critical point. Okay, and as I said, that's in collaboration with Karen Dahman. The paper was published last year in Physical Review Letters. Okay, so what? Why should you care? What does it matter if the brain's at the critical point or not? Well, let me just show you a bunch of these little pictures. Don't worry about all the text. What you'll notice in all these pictures is that you have a function that is an optimal function. It goes up like this. So these are various papers that have talked about information transmission, information storage, computational power, and then also dynamic range, sensitivity to inputs. For all of these categories, very generic models show that being at the critical point will allow you to have optimal responses. So a single cortical column, a unit that is called upon to store information, compute it, and also to transmit information, all of these functions would be simultaneously optimized if it were operating near the critical point. So that implies that if you're off the critical point, you would somehow be unhealthy. Now, people have recently, this is a paper, I think this month actually, in PLOS Computational Biology, people stuck depth electrodes into human patients, and they've done an avalanche analysis of it, and they indeed find things like that. They've even done avalanche shape collapse. Not as good as we would like, but there's signs that maybe if you get slightly better data, you could show it. And so it is relevant for humans. It's been seen in monkeys, it's been seen in many different animals all over. So if being at the critical point allows optimal information, then being off the critical point might lead to neuropathologies. And it's actually not that easy to be at the critical point. If you take a neural network model and just wire it up randomly, it's not at the critical point. If you shuffle the data, you're not at the critical point. If you had small amounts of drugs that tilt the balance between excitation and inhibition, you're not at the critical point. So it's very easy to mess it up. Only certain patterns of connectivity lead to critical operation. And what we found, we've taken some tissue that's been removed from epilepsy patients. Michael Phelps talked about that yesterday. And we can put that on the electrode array, and we find that they have very distorted neuronal avalanches. You're not operating at the critical point. You're operating somewhere in what we would call the supercritical regime. And other groups have also picked up on this. This is just one example. There's other data that seems to suggest that other disorders like Alzheimer's disease and also schizophrenia may also manifest signs that you're not operating at the critical point. So it may have a lot of relevance for human health. What are the mechanisms that lead us to operate within this sweet spot? Just like blood pressure and heart rate and pH all have to be regulated, are there some set of mechanisms in the brain to keep us operating at the critical point? And when they get disturbed, does that lead to neuropathology? So, hopefully I've tried to answer this question. Does it matter if the brain is critical? I've tried to show you what criticality is in a simple system, tried to argue that the neural data at least support this, and that it might be relevant for human health. I'd like to thank the members of my lab, and also our collaborators, Alan Littke for the 512 electrode array. We've been working together for about 10 years. Karen Dahman, condensed matter theory at Illinois. A lot of the data were collected by Shinya Ito and Francis Ye. Nir Friedman and Braden Brinkman analyzed the data. And Tom Butler is the one who said we should look for a universal scaling function. These are the members of my lab. One guy couldn't make it, so he photoshopped himself in. And these are our funding agencies. I'd also like to thank my family who put up with my silly schedule and also give me lots of support. So thank you.